So I'm going to start where we finished yesterday. So just to remind the setting that we have. So now we are in our Lorentz-like setting. So we have remember our map has this shape, and we have two regions, two critical regions which are mapped into the folds. This is delta C, and then we have a similar one here. Delta minus C. We also have, this will not play a very important role, but just to remind you that there is a discontinuity, and this discontinuity is relevant for the dynamics. This is where the derivative is unbounded. This is delta 0. And this part maps to this cusp. This is the cusp. This is the image of the discontinuity. This critical region is mapped to the fold. Okay. Is mapped to the fold. And outside this critical region, we have uniform hyperbolicity. And if you remember the fundamental concept, the geometrical structure that I described yesterday was that of a hyperbolic branch with hyperbolic coordinates, right? And because of the uniform hyperbolicity here, if you take any region that stays outside delta C, then it has a hyperbolic branch. And this hyperbolic branch in general will be long all the way. So I will draw it here for some reason. I could draw it wherever I want, but we will actually, it will be relevant that it contains this image of the critical value, of the image of the critical region, sorry. And if you remember, this has hyperbolic coordinates, so it has this structure, yeah. And the image of this will be somewhere here, so it will be a small kind of small strip here with the stable and the unstable leaves going like this. Okay. And its image will again be here. So part of the, if you remember at some point, I think I discussed the, we can choose as part of the geometric model, we know that this region stays outside for quite a long, we can set this up so that this region actually stays outside for quite a long amount of time. So you can imagine that we have this particular region UK, okay, and it stays outside delta C, and as long as we stay outside delta C, everything is perfect. We get admissible, all these leaves are almost horizontal, the curvature is small, and the same for their images, right? So we have a very nice structure here that we have. Okay, so however, eventually it will return to delta C, okay, and that's what we're going to discuss today, what happens, because we have uniform hyperbolicity outside, but of course most orbits will eventually turn to delta C. If we want, we're looking for some global hyperbolicity, and so we need to discuss what happens when we return to delta C. So I'm going to kind of zoom in here. So I'm going to draw a picture where let's suppose that we have here. Yes? If R is small, as far as I can remember. But anyway, what's the question? So in your system, when R gets large, you have Actually, sorry, yes, of course, you can also, I think when R is small, anyway, in this case, you have a very similar picture like in the Henon map, where because of the fold, you may have some tangencies and you may have some parameters where you have attracting periodic orbits, yes, for sure. So that's what we're fighting against in some sense, just like in the Henon map, yes.
You're totally doomed if the hits delta C in one step, right? That's very critical to protect flies before delta C.
Yes, absolutely. Yeah. Absolutely, yes. Yes. Because you don't want delta C to map back inside itself. Yeah.
That's a surefire way to make the same, right?
Yes. 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 And in fact, we kind of use the fact that delta C takes a long time before the first return occurs. It gives us a bit of a running start, right? Which helps a lot. In the Henon map, that's how you use the fact that you're close, your perturbation with a particularly good parameter value. That's exactly has the same role, that you have a good running start at the beginning for the argument. So what does it look like? So when we eventually come back, we will have that picture. So we will have these unstable leaves are admissible. But for the moment, let's just look at what happens. Let's just suppose we have some admissible curve gamma that is inside delta C. Then we will apply what I'm going to describe to the fact that this is actually the image of some stable leaf, unstable leaf of this. But for the moment, we just look at what happens when you are in delta C. You apply a map F, phi, and so the image of this curve, actually maybe I should use a different color for this curve. So this curve folds, that's the whole point, right? It folds, because that's what happens in delta C. So how do we control the geometry of this fold? In principle, we really don't know much about it except the fact that it folds. But we do have here hyperbolic coordinates, right? So we actually are going to describe the geometry of this curve in terms of the hyperbolic coordinates. So here we have hyperbolic coordinates. In particular, the stable leaves. And at each point, so if you look at this point here, we have these hyperbolic coordinates EK, say, and FK. Okay. And we can look at the tangent vector to this curve, which is the image of the tangent vector to this curve here. So here we have a curve, and here we have the tangent vector. Let me see what notation I've been using. So let's say that this is some point psi. So this is the curve gamma, and this tangent vector is gamma dot, okay, according to some parameterization. So this is the tangent vector at gamma. Then this vector here, let me call it gamma 0 is the image of gamma by the derivative, right? So you take the derivative, sends all the tangent vectors here to tangent vectors here. And so this is gamma 0. Here, gamma dot is the image of gamma dot. And we can write this in hyperbolic coordinates, right? So I'm going to write gamma 0. So here I have, I'm going to zoom in again. So this is gamma 0 dot. This is FK. This is EK. Okay, actually the vectors, I mean, this might be of any length like this, okay? And so let's write gamma dot 0 is equal to omega 0 k sigma 0 k are the components of gamma dot 0 in hyperbolic coordinates, okay, whatever they are. So there is a point, there might be a point of tangency here, right? There might be a point here where this is tangent to the foliation, in which case you would get that omega 0 is 0. Right? This is the horizontal, the expanding component. So because we know, so this is why I emphasized a lot about the admissibility and the curvature and the geometric structure here, right? We know that these hyperbolic coordinates are admissible in the sense that the unstable leaves are almost horizontal and they have very small curvature. This means that the unstable leaves are almost vertical and also have very small curvature, whereas intuitively what I'm going to now say is that this curve here, instead, because of the folds, it maps in some sense with strictly positive curvature, so there is a kind of transversality of the way that this horizontal component of the vector changes as you change the vector. More specifically, the key statement here, the key proposition here is that this horizontal component varies with positive speed. It's a kind of quadratic behavior. So let me say first that we have, suppose we have here a point of tangency. So suppose that here we have Z0. So suppose Z0 is a tangency of gamma 0 with the stable foliation. And then suppose that this is the point Z. Okay, so Z is equal to the pre-image of Z0. So we think of this as kind of a critical point because the image is a tangent. Okay, this actually has a real significance. There is a more formal version in which we call this, in certain cases, the tangencies really, these are like critical points and these are like critical values, okay? But for the moment, let me just use this term informally. So we have our curve that maps quadratically, that maps folds into this region where we have hyperbolic coordinates. We have a point where we have a tangency here, which means that this is the component here is 0. And so the proposition is that for every psi in gamma, we basically have that the horizontal component, omega k 0 at psi 0, okay, so this is the point psi 0. So you look at the vector at psi 0 and the horizontal component, the size of the horizontal component is roughly proportional to the distance between psi and the critical point times the size of the original vector, gamma dot. Okay, so what we're saying here is simply that at the critical point Z, then this is 0, right? Because at the critical point, by definition, this vector will be tangent to EK, so its component here will be 0. And then as you move away from this, right, as you move away from the critical point, you say, okay, how fast does this component change, okay? And this component change proportionately to the distance, okay? This is exactly analog to the fact that if you have a quadratic critical point in a one-dimensional map, then the derivative is just proportional to the distance to the critical point, right? So this is recovering analog. So these hyperbolic coordinates allow us to to make a statement in some sense about how, as you move away from the tangent, see what this component does. And the vertical component, sigma k 0 in size 0, is roughly of the order of gamma dot. So there's not, there's not much change. So one of the differences between one-dimensional behavior near a critical point and two-dimensional behavior is that in one-dimensional maps, you look at the derivative, and when you get close to the critical point, your derivative might collapse completely because you're multiplying by a number that's very close to 0, right? So the derivative, if you hit the critical point, your derivative cancels completely, okay? But here, this is not the case. It's a diffeomorphism. The determinant is not 0 everywhere, so you can, the derivative is not degenerate everywhere. The worst thing that can happen is that you take a horizontal curve and it maps tangent to the stable direction, because what that would mean, remember that the stable direction is contracting, is the most contracted direction for the next k iterates. So if your vector maps tangent to ek, then it will be, for the next k iterates, it will be contracted. So you will lose a lot of derivative. You will lose a lot of length of this vector if k is very large, but you don't lose it immediately at that iterate. In this iterate, it more or less stays well. There is some contraction due to the fact that it's dissipative anyway, but this is just some fixed thing, okay? Whereas if you, so there is maybe a b here, or there's some constant, but it's not, heuristically, the key point is that the size of the vector does not actually shrink, but what matters is the position of the vector in these coordinates. Because, of course, what happens in these coordinates is that the comment I made is that we can understand very well the dynamics, the action of the derivative in these coordinates, right? Now that you have this, if you remember, the derivative has a diagonal form in these coordinates, right? So we look at the image. So now if we apply dfk, d phi k, right, then what is going to happen? We're going to have that the derivative, we're going to get fkk here, right, which is the image of the most expanded direction. And this is expanding exponentially fast because we are in the uniformly hyperbolic region. This is a hyperbolic branch. We have uniform hyperbolicity here. And then the EKK is contracting exponentially fast. And this is orthogonal basis, right? So we have an orthogonal basis here, orthogonal basis here. So we just get a very easy calculation to show us that this is, let's call this gamma dot k, right, which is the image of gamma dot 0 here. So, sorry, I should have put not EKK, but I should have multiplied by the component. Right, this is, this should be omega 0. This should be omega 0 k times fkk, and this should be here sigma 0 k times fkk. I think that's correct. These are the components. Okay, so how do we use this? What does that mean about this picture? So what we really want to do is iterate this picture. So we have this hyperbolic branch after k iterations. So now I'm going to take this hyperbolic branch and I'm going to apply ik to that picture there. And we're going to get this hyperbolic branch, again, is going to contract very much. It's going to, in the vertical, it's going to expand in the horizontal. So we end up with a we end up with a picture with a hyperbolic branch. Looks like this. Because here we have the integral curves of this, right? So we have all the unstable. And here we have the stable, the images of the stable. And what does the gamma 0, gamma k look like in here? Right? This is what we are trying to control. So we want to know what this image looks like, right? And of course, it will just look like a much tighter version of this. So it will have this tangency here, and it will look like a very thin version of this. Okay. So it will still have a fold, right? But depending on, you can calculate, so at each point here, you will have this, you will be able to you will have this picture basically. So this is the zoom in on this picture at this point. This now is the point psi k, okay? And here you have exactly this picture for these vectors, okay? So you can see now, even though I'm not going to write down the calculations, that you can do some calculations here, right? You can do some calculations based on the information you have about fkk and ekk and the slope, right? So if you, you can basically compute quite well, starting from here now, if you look at this curve, okay, and you map all the way to the end there, then you can see that there's a neighborhood of the critical point which is going to fold, but there are, if you're far enough from the critical point, then you will have returned to an admissible situation, right? So there is some small interval here where you still have the fold, okay, so that your vectors could be vertical or almost vertical, but if you are at a sufficient distance, depending on k, on how many iterates you've got, if you're at a sufficient distance, then it means that your horizontal component, your component of your vector in the fkk direction is sufficiently big, and your component in ekk is sufficiently small, so that when you apply this now k times, you end up with something that is admissible, that's almost horizontal, and so you end up getting that this part of the curve is now almost horizontal. It's all admissible. So for this part of the curve, you have recovered the admissibility property. So the conclusion of this whole picture is that if you just take this part of the curve here, okay, you take some parts of the curve that are sufficiently far from the critical point here, then you can guarantee that you return to an admissible situation later. This is really the fundamental final observation from all this. So you are here, so this means that you're looking at this part of the curve, okay? And this means that your horizontal component is non-trivial. You apply, and so you get you get something like this, and then you can show that these are admissible. Okay. So what this does is give us a relationship. You can quantify all these things, right? So you can quantify, at the moment I'm giving just a qualitative description, but you can quantify this, so you can say how far you need to be from the critical point in order that after k iterates, you return admissible, right? So you have k iterates available, so the bigger k is, right? And the closer you can get, because if you have a lot of iterates available, k, you can see that even if this is very, very close to the stable direction, if you're allowed to iterate a very long time, then eventually this will shrink enough, and this will grow enough, and you will return to an almost horizontal position. So So it's really a question of how close you are to this point of tangency is what determines whether using the information you have of this hyperbolic branch at time k, you can recover. Okay, so this is the point I want to make now, because I'm trying to bring us to a kind of condition on the parameter, remember? So we are trying to describe what a good parameter looks like. And a good parameter, I'd like to start saying, I'm going to say a little bit more. Now we're going to concatenate a lot of these hyperbolic branches, but as a very first approximation, you take this hyperbolic branch, you iterate it, right? And at some point it comes back into delta C, or you should imagine this a little bit thinner. It comes back to delta C, and then you map it into this fold. And if the image of this hyperbolic branch is just contained in this region, actually, it doesn't cut all the way across. If it maps into this region at time k, okay? So at time k, because at time k, you have information about k. So you know that until time k, you're okay. So you have your hyperbolic branch. And if at time k, it maps at a sufficient distance from the tangency here, then you can wait k more iterates, and you come back to an admissible, and you can just keep going, and then you stay outside, and then you wait till the next time that you come back. So let me try to say this a little bit more formally, although I really don't have that much time, but we can have we can concatenate these hyperbolic branches. In other words, you can repeat this. So let's suppose that we have this picture where we have a family of hyperbolic branches, phi pi u, phi pi u pi. Okay, for I equals 1 to L. You have a family of hyperbolic branches. And then we have one hyperbolic branch, phi n un, okay, that has this property that we have, and then we have some sequence of times, 0, nu1 plus p1, nu2 plus p2, and so on, up to nu L plus pl up to n. And the picture is the following, is that you start with this hyperbolic branch, and you stay outside delta, so phi n, so we have this property. So phi I of un, this is our hyperbolic branch that we're really studying, and these are the hyperbolic branches that we're going to fall into every time we fall into delta C. So we have that this does not intersect delta C. This is empty for all I before time nu1, and then before time nu1, and then at time nu1 you fall into the branch, so phi nu1 of un falls into delta C, okay, and so maps into delta C, and in fact, and the next iterate will fall exactly into the first branch. So phi nu1 plus 1 of un falls into u p1. Okay, so we have exactly this picture. So we fall into delta C, and then we fall into the first one of these hyperbolic branches, and then we assume that at the end of this we've recovered admissibility. So we assume that we are fortunate enough that we came not too close to the tangency, so that within P1 iterates that are available to us, we return admissible. So then we have phi nu1 plus P1 plus 1 of un is again admissible. Okay, and then we stay outside delta C, so then phi I of un intersection delta C again is empty for all I between nu1 plus P1 plus 1 and nu2 Okay, and then the same thing happens. So I will not write this down. So the idea, this is each time, so I'm not explaining how it's possible that that may happen, but you start with this hyperbolic branch, and it stays outside delta C, then it falls in delta C, and then we assume that it falls into a hyperbolic branch, and it satisfies this kind of bounded recurrence condition, we call it, to this tangency, so that we survive, and then we, for P1 iterates, we stay inside, and then we're outside, we spend some more time outside, everything is good, it continues admissible, then it falls in delta C again, and then by miracle we say, wow, amazing, it falls in delta C, and it falls in the fold, and again, it falls somewhere where you then, the next iterate is inside some other hyperbolic branch, and it's a good distance so that it recovers admissibility again. Okay, so this is what you'd like to happen, right? So if you get all this, then you're done. So basically, we have this situation that at each, so basically at each return to delta C, we have that the image falls into some UPI, okay, and the recover admissibility, so recover admissibility at the end, after PI. So in some sense, it's a bit unsatisfactory not to be able to give some more geometrical details, but in some sense this should be used intuitively as the definition of a good parameter. So a good parameter is one where this always happens, okay? So in some sense, the parameter exclusion argument, although there's a huge number of elements which still need to formalize this, is about looking at this geometric construction and then looking at a parameter, and every time you fall back into delta C, you say, okay, is it good? You know, in other words, does it satisfy that condition? If it's good, it's a good parameter. If it's not good, you throw away the parameter, okay? And then you keep going. So because I have only very limited time, what I want is to give you a little bit of an idea of how, in fact, you then throw away the parameters and how you do it, how you end up showing that there is a positive Lebesgue measure set of parameters for which you can do this forever, right? That's the goal. And then you can kind of believe, when I said that you have a hyperbolic structure, this is what I mean, right? In the end, for a good parameter, you will choose a good parameter so that you always have this very good control. Every time you come back to the critical neighborhood, you then eventually recover, and that's how you get the non-uniform hyperbolicity that you need then to construct the physical measure, the SRB measure. Okay? So I will just use my last few minutes to give you a very intuitive idea, and going back to the one-dimensional map, I think now I will say something about this bounded recurrence condition in the one-dimensional map, and maybe it can give a little bit of a feeling. Yes? Sorry? Okay. So the one-dimensional map, so let's just briefly touch on the parameter exclusion argument. So if you remember, the one-dimensional map looks like this. So we have the discontinuity, and we have the one-dimensional map of the diagonal. And these are the two critical points here, C and minus C. Here you can see very clearly this observation about why the fold is below the diagonal, which corresponds exactly to this fold being to the left of the critical point here. And then we have these neighborhoods, delta C, a neighborhood of minus C, delta minus C. And then we have a neighborhood of the discontinuity, which we need to worry about, which we call delta 0. And this completely symmetric. So in fact, what we're interested is following the orbit of C, which is a little bit like following the orbit of the critical region here, or rather the image of C. So we write C0 is equal to the image of C, and then we write Cn is equal to Fn of Cn. So the connection between the one-dimensional and two-dimensional is not completely obvious. So I'm just trying to give a heuristic picture of what's going on. So the good parameter, so what I've been trying to do geometrically describe a good parameter is very easy to define in the one-dimensional because I can define it like this. So it's a parameter where we have uniform expansion. It's uniformly expanding outside delta C, delta plus or minus C, okay? And it satisfies the following, what we call a bounded recurrence condition, which has the following form, the product. So you look at all the I from 0 to n minus 1, and you look at all the times that the image of the critical point falls into either the critical or the singular neighborhood. So you look at the image of the point C, and then you look at all the times it falls in here, and when it does, you take the distance. So this notation here means that you take the distance. If it falls, if Ci falls in delta C, then you take the distance here. If it falls inside delta 0, you take the distance to the singularity. If you take here, you take the distance here. As I mentioned here, what is important is the distance. This kind of geometric critical point here corresponds to the critical point here. And we want that this is greater than or equal e to the minus alpha n for some alpha that can be chosen small. So this is a condition, if you think about it, these are all very small numbers, right? Because we have very small neighborhoods here. And what this condition is telling you is that it's relating how close you're allowed to come to any of these 3 points in terms of n, right? So this is a product of small numbers. So in particular, what it says is that for each return has to be bounded by this, right? So when n is very large, you're allowed to come very close. And it takes into account the history a little bit. So the reason for the product, it says, okay, you've used up some of your credit. If you came up very close, as close as you can in the past, and you're still not allowed to come, then it means it puts a stronger condition on how close you're allowed to get. But essentially, it's telling you that at time n, you're not allowed to get closer than e to the minus alpha n, okay? And the main lemma in the one-dimensional, it's fairly easy to show, is that 1 plus 2 implies that the derivative along the critical orbit, so the derivative of this one-dimensional map at the point C0 is bounded below by some exponential, some fixed exponential lambda. And because you're controlling the recurrence also to the singular region, it's also bounded above by some e, some big lambda here, okay? And that is important for various technical reasons that you have this maximum derivative growth here. So these two conditions, they imply that this derivative is going exponentially fast, and by some relatively standard constructions in one-dimensional dynamics, if you have this property for all n, then you can construct a physical measure, an absolutely continuous physical measure. So this is kind of the definition of a good parameter, right? These two properties, because they imply this property, which is a very good property to have. And one, so notice that one is an open condition. One is an open condition. Okay, so you take a range of parameter values and it will continue to hold. So the real parameter exclusion, the condition on the parameter is this one. Okay, we call it condition star n at time n. So this is the condition that's going to decide at each time whether this parameter is good or not, right? So you follow, for the different parameter values, you follow the orbit of the critical point, and then if it satisfies this, it's good. If it fails to satisfy this, so if it comes back too close, then you throw away the parameter. And so 2 is the condition on the parameters. Okay, notice this is just quantifying a bit more precisely what I intuitively said here. So this is the exact bound on how close you're allowed to get in terms of, here I used k, that it's n, it's the same thing, right? So that condition is telling you that you're allowed to get close up to that much, and if you get close, if you get any closer than that, then this number of iterates you have available is not sufficient to recover your derivative. In this case, it's more than the derivative, it's the admissibility, a bunch of geometric properties, but essentially it's the same. But if you're far enough, then it's okay. Okay, so this is the condition on the parameters. So how do you show that many parameters satisfies this condition? So I will just give a very, very brief intuitive idea, and there's a key lemma. So if omega is a parameter space, okay, then what we have here is so what the parameter does in this map is it just translates these up and down, okay? What it does here is it just translate this to the right, to the left. That's what the parameter does. So the critical point actually stays the same, okay? But the critical value depends on A, right? So in fact, we have, if omega is a parameter space, then we have C0 of A, okay? When A is in omega, we have a family of critical values. So for each critical point, you get a critical value that depends on A, right? So A shifts is up and down. So the image of this has a little interval. And then we have correspondingly the other, so we can write omega n is just equal to Cn of A for A in omega. So we have an interval of images, right? So here, now we look at the image of the critical point, and of course, because the map is smooth and depends smoothly on the parameter, you will get an interval. So at some point n, you look at the images of all the critical points and you get some interval here. Okay, you get some interval here. And the key lemma the remarkable key lemma here is that if you satisfy condition star, then you have the property that the derivative with respect to the parameter, so since you have at time n, you have for each parameter, so here you have your parameter space omega, you have this map, basically Cn, that associates to each parameter A the image of the critical point under that parameter value. You get some interval in here, and then you can talk about the derivative with respect to the parameter. So if you change A a little bit, how much does this change? And the amazing thing is that this is actually of the same order as the derivative with respect to the phase space at C0. And what this means is that because you are controlling, if you satisfy this condition, then the derivative with respect to the phase space is going exponentially fast, which means that also the derivative with respect to the parameter is growing exponentially fast, okay? And that means that your interval, so, okay, a consequence is that omega n is growing exponentially fast. It's growing, right? So it's large. And the fact that it's large, okay, essentially means that if now you look at Cn omega, it's large. So what does it mean, large? Intuitively, the fact that it's large means that it's kind of uniformly distributed. It's not that large. It's not the whole thing, but it means it's very large. So now, what is this condition here? You want to see which of these parameters fail this condition here, and which ones do not fail this condition here. And this condition here says that you're not allowed to come very close, right? This is something of the order of e to the minus alpha n. So at time n, you're not allowed to come in here, okay? So the fact that omega n is growing means that it's very large, and it means that it's only very few. So if suppose your omega n is this big, okay? So then, okay, you know that some of these might fail, but it is a very small measure of this that falls in there. And that's why you will throw away now a very small set of parameter values, right? So roughly speaking, this implies that Cn of A is, let's say, in some sense, kind of randomly distributed. Randomly distributed, okay? And this implies that we have a small probability, of failing condition star. And this is actually, this is a heuristic, but this is actually the argument. This final part of the argument is indeed kind of probabilistic in the sense that you do not know exactly which parameters you're throwing away and which ones you're not throwing away, right? So in the end, what you show is that at every n, okay, you can have an estimate because you control the sizes of these things, right? And Fn is growing exponentially, and therefore this is growing exponentially. So even though you have very small parameter intervals, their images tend to be very big, and so you're throwing away a very small percentage here, and so very small percentage here. So you're throwing away smaller and smaller pieces here because they are the pre-images of these tinier and tinier intervals. And it's like the construction of a Cantor set of positive measure. For those of you who are familiar, when you construct a Cantor set of positive measure, you just throw away smaller and smaller intervals, and what you're left with is a positive measure subset. So this is really the two, in some sense, this is the one-dimensional argument basically is this, okay? It's not a trivial argument, but when you compare it to the two-dimensional, it feels very, very simple. The biggest additional ingredient and the difficult thing going from one dimension to two dimension is that here you can just, the critical point is well defined. You can talk about the distance, so you can define a good parameter right from the beginning. You can say, these are the parameters that I'm looking for, okay? And then you work to make sure that a lot of parameters satisfy this. The big step that we need to do in the two-dimensional part is that when we come back to delta C, we don't know what the critical points are. We don't know what the distance is. So that's why we introduce all this hyperbolic coordinate framework that allows us to define very clearly what these points of tangencies correspond to some approximation to the critical point, because when you fall here in the critical point, you're lost forever, okay? Here in theory, you don't know, because you only know that up to k iterates you contract, but then you may recover again. But you use this as a kind of step-by-step procedure, so every time you come back, you make sure that you're a sufficient distance from the critical point in the same, essentially the same condition there. That allows you to recover the geometric properties, and then when you come back again, you assume you have that. And so then you need some kind of much more sophisticated analog of this to tell you that for different parameter values, you kind of also have a similar probability where very few parameter values will actually end up here. And then you have the added complication that you will have many such critical points. There is a kind of vertical distribution here, so that when you come back, you might come back to one critical point or to another critical point, but this is just to tell you that there's more geometrical complications. But I think the fundamental tools are this picture of hyperbolic coordinates, and then finally this probabilistic argument for the parameters. So I think I finish here. Thank you very much for listening. Thank you. I wouldn't be able to answer any questions at this point.
Okay.
They would be too, they would require a whole nother lecture to, any question at this point would require an hour to answer, so.
Okay, so let's thank Stefano again.
Thank you.